We're still talking about the numerical integration, and in this video we will give a very good example on an actual case that has a very good engineering background. Before we go through the integration and all this stuff, I'm just gonna spend a couple of minutes discussing the problem that we are gonna solve. So we discussed before in the previous video the flow through orifice, and we mentioned how the flow goes and how these equations came from Bernoulli equation, and that we can calculate the flow rate using this equation, and the term dH by dt, which is the change of height with time, can be calculated from this equation. And it was kind of straightforward thing. You just and we saw how we can use ode45 to solve this equation. And this equation was reached this form of this red equation by assuming that this is an open tank, and this open tank is maintaining the pressure all the time here as 1 atmosphere, and that's why we were able to get rid of all the pressure terms in between these 2 points before, or inside the tank and outside the tank, because both are atmospheric, and that's why we didn't have any pressure term in this final form. However, the problem that we are going to discuss today is when the tank is closed. So let's assume that this is the same thing. You have liquid in a tank and the tank is closed, and you open this orifice and the flow starts to come out of the tank. And you'll notice that the behavior would be the same in the beginning, but as the time passes and the height goes down, there will be a vacuum here. The pressure will decrease here because this is the same amount of gas inside this space, and the space increases, and we know that as the volume increases, the pressure decreases for the same number of moles. So what we expect is that you will have smaller flow rate coming out of the nozzle as time goes on. And to get a mathematical way to describe this, we will go with the same steps that we mentioned before. We will start with Bernoulli equation. Between this point and this point, we will have some assumption that the same assumption that the height is changing, or the velocity of the height is very small compared to the velocity here, and that the pressure here is atmospheric, and we will take our datum here. So the equation would end up with this form. The pressure, of course, will not get rid of the pressure here because P1 is a variable now. So P1 over gamma plus H equals, which H should be, at any time T, this will be H. So I mean this height is going to be equal to P2 divided by gamma plus V2 square over 2G. And again, if you do the same thing, just get V2 on one side just to get the Q. So we can say that Q equals V2 multiplied by CD A node. So V2 can be got as this form, which is we will substitute by Q as the area by area multiplied by height divided by time. So this is going to be AT, which is the area of the tank, and this is CD A node. A node is the area of the orifice, and this is the dH by dt, which is the change of height with respect to time. So at the end of the day, we'll put pi over 4d square and pi over 4d square. We will end up with this form, which is negative 1 over CD d capital over d small power 2 multiplied by dH by dt. Of course, it's kind of different now. And when we substitute here, we will end up with this form. Just put this in here, and by substituting and by simplifying the equation and getting dH by dt on one side, you will end up with this form, which is negative 2g under the root multiplied by g cd d divided by d multiplied by 2 multiplied by p1 over gamma plus h2 minus p2 over gamma all power 0.5. Of course, this is a general form, and the previous case is a special case. So in case you want to get the general form or the special case from the general form, you just put P1 equals P2, so these terms would cancel out, and then we will end up with h power half, which is gonna go here, and you will end up with the same shape of this equation. So it's gonna be the same thing if P1 over gamma equals P2 over gamma. Now I cannot solve this equation as is because I have two variables here, dh, which is h, the dependent variable, and t is the independent variable. But I know p2 is constant, but I have p1 here, which is a variable, and I cannot solve these equations or this equation numerically with this variable here. So I have to get rid of this p1, and to get rid of this p1, you can simply find the relation that relates height to the pressure. And you can simply assume that this gas here is an ideal gas, or it behaves ideally. And this is going to be a very valid assumption if the pressure is low. And I'm assuming that I'm working with or starting with 1 atmosphere or 2 atmosphere, which is not very high pressure. So assuming that it is an isothermal process, so P1 multiplied by V1 at T equals 0 equals P1 multiplied by V1 at any time T. And I'm assuming that I know this information, HT and H1, and I know the diameter, so I know exactly the volume in the first, or in the very beginning, and I know the pressure in the very beginning because these are the initial conditions that I'm gonna start with. So I can know from any height what is the volume. So I can say that V1 equals P1 V1 at t equals 0 divided by P1 at any time. This is what I did here. I just substituted by V1. So V1 is going to be the height multiplied by the area. The area is pi over 4d square, which is going to be the same on both sides. And the height is going to start with ht minus h1, which is the height of this white part, the white rectangle. And here's going to be ht minus any height h. And from this you can say that, of course, pi over 4d squared is going to cancel out on both sides, and then we will end up with P1 equals ht minus h1 divided by ht minus h. And we say that ht is the total height of the tank. H1 is the height of the liquid in the very beginning at time equals 0, and the h is the height at any time t, height of the liquid at any time t. And then by substituting here, you would get that P1 here and put it there. It's going to be P1 at time equals 0 divided by gamma and multiplied by this term. So this is how I can describe the change of height with respect to time in case you have a closed tank. So now we want to see how this will affect the integration. And this is going to be a very good exercise actually, because it's not only showing you how to solve the equation different times, but it also gives you a feeling of the numbers. And we will see in a few minutes how we can tell that these numbers make sense or do not make sense. So I'm gonna go now to, I'm keeping the equations here just because we are gonna use them. I need just to move this a little bit up to make sure that you can see everything and that my part of the video that's showing my face is not hiding anything. This is it. So I think the equation is easy to see now. So I'm gonna open a new M file so that I can write everything in one place and don't need to put any more information. So I'm gonna start by clear CLC, close, and then start with givens. So the givens here, let's say that I have P1 equals 1.013 multiplied by 10 power 5, and this is gonna be Pascal. I'm gonna put P2 equals, I'm gonna put both as 1 atmosphere just for now, and then we will change them later. I have 3 H's, so I have HT, which is the height of the tank. I'm gonna put it at 15 meters. And then I have H1, which is the initial height of the liquid. I'm gonna start with 13 meters. And then we have G equals 9.81, and this is meter per second square. We have the gamma or the density. I'm gonna put it as 1000, assuming that this is water, and this is gonna be kilogram per meter cube. Gamma is gonna be G multiplied by density, so that we have the both multiplied together. I think everything is, I have CD, I'm gonna put it as 0.8 for now. What else? I think this is all the givens that we have now, so we can start with writing the equation, the equations. So I'm gonna start first with the open tank, which is the simple case. I'm gonna say that the H open, for instance, O, which is refers to open, is gonna be ODE, or I'm just put it as the function handle at, this is gonna be function of time and height, and the equation is gonna be negative CD multiplied by square root 2 multiplied by G multiplied by H, and that's it. I'm gonna just get the use the ode45 function to get the time open, and the height open is gonna be ode45 dho. I'm gonna start with the time span from 0 to just I'm gonna put t in here, so that is just one number. I'm gonna make it like 500 now. Oops. And make sure that this is in the proper units. This is gonna be in seconds. So when I put t end here, I know that this is in seconds. And I'm gonna put the initial value, which is the h1, which is the 13 meters, and that's all. I don't want to see the numbers, I want to see the plot. So I'm gonna ask him to plot the t open versus the h open, make it red and solid, and put square markers. I'm gonna make the marker face color red as well, and I'm running. I'm getting to run it now. So I'm just calling it tank 1, and it's now saying it's busy here in the bottom. I'm not sure if it's I think something is not right, because it shouldn't go this way. It should go like this, and it's going way down than it should go in the actual case. So I'm just gonna revise the equation. It's negative CD. Oh, I didn't multiply it by d over d square. So this is good that I did this mistake. So I didn't put part of the equation, and it messes up everything, because it's d over d is going to be a very small number. So assume that I have the small d as 0.1 meter, which is 10 centimeters, and the capital D, which is like 2 meters. So it's very big ratio, or very small ratio. It's 0.1, it's 1 over 200 power 2, so it's going to be very huge difference. So when I run the file now, it says that something in column 17. Oh, I'm sorry. It is d divided by d, and now when we run, oh yeah, now it looks good now, and this is what we should expect to see, that the height is starting at 13, it's going slowly downward, and it didn't reach the end now, so I can let it go more. I just want to put x label height in meter, and y label it's gonna be time in seconds, and just want to put the time that it ends at, I think I put it, yeah, it's here, the end time, and make it like 800 instead of 500, and I'm running the file, and now you see it's almost empty now. So it reached the point that the height is equal to 0, and you see that the points here are getting very close. compared to what we saw here. And this is why when it gets to 0, the integration starts to be kind of difficult, and there would be some imaginary numbers, so it's making the step very, very small so it can get some reliable results. So this means that when you see this, it means that you're done. The tank is empty, or you reached the asymptote, the last value that you're gonna reach. Um, so this is the first part, and now let's go to the second part. Is we are gonna repeat everything. So I'm gonna make a copy of this and do for a closed tank. And I'm gonna make DC DHC and make it DHC, and the difference would be just in this part, which is the equation. It's um, negative CD multiplied by D by multiplied by divided by D power 2, multiplied square root 2G, and then there are other terms here. So instead of H we have this bracket here. So this bracket I'm writing is exactly the same thing here. So it's gonna be P1, which is the initial value of P1, divided by gamma multiplied by HT minus H1 divided by HT minus H. So this is this part, and then plus H minus P2 divided by gamma. So this should be it. This is all in the square. I just want to make sure that HT and H1 are exactly the ones I'm writing well. So this is HT, H1. Okay, this should be right. We'll check. Yeah, you never know if this is right or wrong. So I'm just make this DHC. So it's now I'm gonna make this T closed and this T H closed, T closed, H closed. Make this black, and this is black as well. I'm not gonna put these anymore. I just wanna make sure that everything is gonna be kept as is. So I'm putting red, and I am holding the plot. So this is important to see that everything is in place. The last thing to put is to make a legend so you understand which is which. So I have two things here: open tank and closed tank. So I'm gonna run the file now and see if I'm getting any error messages. And now it's working fine, and this is what I'm expecting to see. When you have the tank closed, as you go forward the pressure decreases, and as the pressure decreases you would have back pressure, which or a pressure that is or a vacuum that is pulling the liquid inside the tank. So the tank will not be totally emptied when you have the tank closed. It will reach a point when it will be reach the height. So now the pressure on this side equals the pressure on this side, so the tank cannot put any more or drain any more fluid. Let's try. So now the final height is almost 7.5, something like that. And now let's see if I change the pressure P2. I'm gonna make it like 2 times, 2 atmosphere. And when I run the file, I think I did something wrong. Let's oh, it's not P2, it's P1. I'm sorry. I'm gonna make P1 2 multiplied by 1 atmosphere. And when you're in the file, you'd see that, and this is amazing actually, that you see that the first thing that you notice, that at this point in the very beginning, the flow rate of the fluid coming out of the orifice is higher for the closed tank, because you have more pressure. It's not only 1 atmosphere, it's 1 atmosphere. It's 2 atmospheres actually. It's double the pressure. So the height is getting lower quickly here. And then the second thing is that the final height is getting lower. It's almost almost 6, and in the previous case it was 7.5. So it's like almost 2 meters or less than 2 meters difference in the final height of the float. So it's a very good exercise to do, and to rationalize the numbers that you see, and make sure that you understand that this is the output and this makes sense or doesn't make sense. And as you saw, when I did a mistake and put P2 as double, I saw the numbers going in a weird way. And let's I'm glad that I did this mistake, because if you look at this, you'd see that here it doesn't matter actually, because the pressure didn't appear in any part in this equation. So it doesn't matter if even if it's like 10 times, it's not gonna make any difference. But here you'd see that it's making a big difference, because here you'd see that the pressure on the other side is higher, so the float cannot, or the pressure head cannot push the liquid to overcome this very high pressure. So this is important to make sure that you understand the number and how the numbers affect the system, and you would expect that output, and know that something is going wrong if it's not giving the output that you are expecting, or to draw your attention to some parameter that you didn't think about before. So I hope this is useful, and I'll see you in the next video, inshallah. Goodbye.